Hello, cloud gazers, weather watchers, and curious minds from wherever you are listening. Welcome to this journey into the fascinating world of clouds and the science behind their breathtaking displays. Today, we'll unravel the mysteries of the sky, exploring the whispers of the wind, the dances of water vapor, and the artistry of nature's own paintbrush. Look up, take a moment to truly see the clouds, those magnificent, ever-shifting forms drifting lazily across the vast canvas of the sky. Are they fluffy cotton balls, towering castles of ice, or somber, brooding storm clouds? Each cloud is a unique masterpiece, a fleeting moment captured in the atmosphere. Their ethereal beauty inspires awe, a sense of wonder that connects us to something larger than ourselves. Their shapes shift and change, constantly morphing under the influence of unseen forces, wind currents, temperature variations, and the subtle interplay of water and air. They are living entities, in a way, dynamic and alive, whispering secrets of the atmosphere to those who take the time to listen. Today, we embark on an exploration of these celestial wonders. We'll delve into the science behind their formation, the various types that paint the sky, and the profound role they play in our weather patterns, our climate, and even our cultural narratives. From the delicate wisps of cirrus clouds high above, to the heavy, pregnant cumulonimbus clouds that herald a storm, every cloud holds a story waiting to be told. We'll uncover the intricate processes that govern their birth, their evolution, and their ultimate dissipation, revealing the hidden mechanisms that drive these atmospheric marvels. Prepare to be amazed by the complexity and beauty of these airborne phenomena, and to understand the intricate connection between the clouds and the world below. This is more than just meteorology. It's a journey into the heart of nature's artistry, a testament to the incredible power and subtlety of the natural world. So, let's begin to unravel the whispers of the sky and discover the secrets they hold. A journey that will take us across continents, through time, and into the very fabric of our atmosphere. And at the end of our journey today, you'll be able to look up at the sky with a much deeper appreciation for the stunning, ever-changing canvas above. For millennia, clouds have captivated humanity, inspiring awe, wonder, and a deep-seated curiosity. Long before the advent of scientific instruments and meteorological understanding, clouds held a mystical significance, woven into the fabric of our myths, legends, and artistic expressions. They were, and in some ways still are, enigmatic entities, their ever-changing forms prompting speculation and interpretation across cultures and time. Imagine the ancient mariners, their lives inextricably linked to the whims of the weather, gazing upon the heavens with a mixture of hope and trepidation. The clouds, to them, were not merely atmospheric phenomena. They were harbingers of fortune, symbols of divine power, or ominous signs foretelling storms and tempestuous seas. Their movements dictated the success or failure of harvests, the safety of voyages, and the very rhythm of daily life. In countless mythologies, clouds are imbued with symbolic meaning, often associated with deities, spirits, or celestial beings. They are the chariots of gods, the breath of dragons, the tears of angels, powerful metaphors reflecting humanity's attempt to comprehend the forces of nature. From the swirling storm clouds of Zeus to the gentle rain clouds associated with benevolent deities in various cultures, clouds became integral parts of spiritual narratives, shaping our understanding of the world and our place within it. Ancient artists, lacking the tools to dissect the scientific processes behind cloud formation, captured their essence through evocative imagery. Cave paintings, frescoes, and early landscapes depict clouds as dramatic backdrops, ethereal veils, or ominous presences, reflecting the emotional and spiritual associations clouds held for their creators. These artistic representations provide a glimpse into the minds of those who lived in closer proximity to the natural world, their understanding shaped by observation, intuition, and a deep connection to the elements. Early attempts to understand the nature of clouds were often interwoven with philosophical and religious beliefs. While scientific understanding was limited, keen observers noted patterns and correlations, developing rudimentary forecasting methods based on cloud formations and their associated weather patterns. These early efforts, though far from the sophisticated models we possess today, represent the beginning of a long and fascinating journey towards understanding the mysteries of the sky. The enigma of the clouds, therefore, is not merely a scientific puzzle. It is a testament to humanity's enduring fascination with the natural world and our ongoing quest to decipher its secrets. The journey from myth to modern meteorology is a testament to our ever-evolving understanding of the skies above. We often look up at the sky and see magnificent clouds, towering cumulonimbus or delicate cirrus, but the true magic begins with something invisible: water vapor. It's the unseen architect of those breathtaking formations, the fundamental building block of every cloud, a crucial element in the Earth's intricate water cycle. Think of the air around you. It's not just empty space. It's a dynamic mixture of gases, and among them, a vital component often goes unnoticed: water vapor. This is water in its gaseous state, invisible to the naked eye, yet constantly present in varying amounts depending on temperature and humidity. It's the air's hidden reservoir, a vast, invisible ocean suspended above us. The water cycle, a continuous process of evaporation, condensation, and precipitation, relies heavily on this invisible ingredient. As the sun warms bodies of water, lakes, rivers, and even the damp earth, water molecules transform into water vapor, rising into the atmosphere. This process of evaporation is a constant, silent exchange between the Earth's surface and the atmosphere above. The amount of water vapor the air can hold depends on its temperature. Warm air, like a sponge, can absorb more moisture than cold air. As warm, moist air rises, it cools, and its capacity to hold water vapor decreases. This cooling process is crucial for cloud formation. Imagine a glass of iced water on a warm day. Condensation forms on the outside as the surrounding air cools and releases its moisture. A similar process occurs in the atmosphere on a much grander scale. As the rising air cools, the water vapor reaches its saturation point, meaning it can no longer remain in its gaseous state. At this point, the water vapor begins to condense, clinging to microscopic particles in the air, dust, pollen, salt, forming tiny water droplets or ice crystals. These minuscule droplets and crystals are the seeds of clouds, the first visible manifestation of the invisible water vapor. Billions of these tiny particles cluster together, growing larger and larger, eventually becoming visible to our eyes as the clouds we so readily admire. Understanding water vapor is key to understanding clouds, weather patterns, and the delicate balance of our planet's climate. It's a reminder that even the most spectacular phenomena often begin with the unseen, the subtle processes occurring constantly around us, shaping the world we inhabit. The invisible ingredient, water vapor, is the silent architect of the magnificent spectacle we observe in the sky. Now that we understand the crucial role of water vapor, let's explore the dynamic process that drives cloud formation: the rise and fall of air. Imagine the atmosphere as a vast, invisible ocean, not of water, but of air. Within this ocean are countless air parcels. Think of them as invisible balloons, each containing a mixture of gases, including water vapor. These air parcels are constantly in motion, influenced by temperature differences and atmospheric pressure. Warm air, being less dense, tends to rise, much like a hot air balloon ascends. As it rises, it encounters lower atmospheric pressure, allowing the air parcel to expand. This expansion is a crucial step because as the air parcel expands, it cools. Think of it like this: when you quickly release compressed air from a can, it gets noticeably colder. The same principle applies to our rising air parcel. This cooling is the key to cloud formation. As the air parcel cools, its ability to hold water vapor diminishes. Remember, cold air can't hold as much moisture as warm air. So, as the air parcel continues its upward journey, the water vapor within it reaches its dew point, the temperature at which it condenses. This condensation doesn't happen spontaneously. The water vapor needs something to cling to, a surface, however tiny. These surfaces are provided by microscopic particles in the air, dust, pollen, sea salt, even tiny bits of volcanic ash. These particles act as condensation nuclei, providing a platform for the water vapor to transform from an invisible gas into tiny liquid water droplets or ice crystals. The process is akin to a bustling city. The rising air parcel is like a busy street, with countless microscopic particles acting as buildings and gathering places. The water vapor molecules, initially scattered and invisible, are like people seeking shelter from the cold. As the air parcel cools, these molecules find refuge on the condensation nuclei, forming a visible crowd, a cloud. The size and shape of the cloud will depend on various factors, including the amount of water vapor present, the rate of cooling, and the type and number of condensation nuclei available. But the fundamental process remains the same: rising air, expanding and cooling, leading to condensation and the creation of clouds. This upward motion, this constant dance of warm air rising and cool air sinking, is the engine that drives the ever-changing canvas above us. It's a continuous cycle, a testament to the dynamic nature of our atmosphere. And it all begins with the seemingly simple act of air rising. We've learned how rising air cools and water vapor condenses, but this process wouldn't be possible without the often overlooked heroes of cloud formation: condensation nuclei. These are tiny, microscopic particles floating in the atmosphere, acting as the essential scaffolding upon which clouds are built. Imagine them as the seeds from which clouds sprout, each a tiny platform for water molecules to gather. These aren't just any particles. They're a diverse collection of substances, each contributing its unique properties to the cloud formation process. Some originate from the Earth's surface, lifted into the atmosphere by winds and updrafts. Think of dust particles, stirred up from arid deserts and carried vast distances by the wind. These tiny grains of sand, clay, and minerals provide abundant surfaces for water vapor to condense. They're like microscopic islands in the vast ocean of the atmosphere, attracting and accumulating water molecules. Pollen, released by flowering plants, contributes significantly to the number of condensation nuclei. These tiny grains, carrying the genetic blueprints of future plants, also play a crucial role in cloud formation. They're like tiny rafts, each capable of supporting the weight of countless water molecules, contributing to the growth of cloud droplets. Ocean spray, whipped into the air by winds and waves, provides another major source of condensation nuclei. Sea salt, a natural byproduct of ocean evaporation, forms microscopic crystals that readily attract water vapor. These tiny salt crystals are like miniature magnets, drawing water molecules to themselves, helping to build clouds above the oceans and near coastal regions. Even volcanic eruptions, while often destructive on the ground, contribute to the atmospheric supply of condensation nuclei. Volcanic ash, composed of finely pulverized rock and minerals, is ejected high into the atmosphere, providing countless nucleation sites for cloud formation. These particles, originating from deep within the Earth, contribute to the atmospheric tapestry in unexpected ways. Beyond these natural sources, human activities also play a role, though often an undesirable one. Pollution in the form of aerosols and soot particles can increase the number of condensation nuclei. These particles, though often detrimental to air quality, can also influence cloud formation, sometimes leading to changes in cloud properties and weather patterns. So, the next time you gaze upon a cloud, remember the countless microscopic particles that make it possible. These tiny seeds, often invisible to the naked eye, play a vital role in the beautiful and complex process of cloud formation. They are the unsung heroes, the tiny architects of the ever-changing sky. Their presence and abundance profoundly influence the clouds we see, highlighting the intricate interconnectedness of Earth's systems. We've explored the microscopic world of condensation nuclei, those tiny particles that act as platforms for water vapor to gather. But what triggers the actual transformation of invisible water vapor into visible clouds? The answer lies in a crucial concept: saturation. Imagine a sponge slowly absorbing water. Initially, it eagerly soaks up the liquid, becoming wetter with each drop. But there comes a point when the sponge is completely saturated. It can't hold any more water. The air behaves in a similar way with water vapor. The air has a capacity to hold a certain amount of water vapor, depending on its temperature. Warmer air can hold more water vapor than cooler air. Think of it as a larger sponge. As warm, moist air rises, it expands and cools. This cooling process reduces the air's capacity to hold water vapor. It's like squeezing the sponge. The water has to go somewhere. As the air cools, it eventually reaches its saturation point. At this critical juncture, the air can no longer hold all the water vapor it contains. The excess water vapor must condense into a liquid state. This is where the condensation nuclei step in, playing their crucial role. The water vapor molecules, now having nowhere else to go, cling to the surfaces of these tiny particles. As more and more water molecules condense onto a nucleus, a tiny droplet forms. This is the birth of a cloud droplet, a miniature sphere of liquid water. Millions upon millions of these tiny droplets form simultaneously, clustering together to create visible clouds. The size and density of these droplets determine the cloud's appearance. A collection of small droplets creates a delicate, wispy cloud, while larger, more numerous droplets form denser, more imposing clouds. The process of saturation isn't a sudden event. It's a gradual transition. As the air continues to cool and more water vapor condenses, the cloud droplets grow larger and more numerous, creating the spectacular cloud formations we see in the sky. The beauty and variety of clouds are a direct consequence of this delicate balance between the air's capacity to hold water vapor and the process of saturation. It is a continuous dance between invisible vapor and visible cloud, a testament to the dynamic nature of our atmosphere. The next time you see a cloud, remember that it's a visible manifestation of the air reaching its saturation point, a dramatic display of nature's remarkable equilibrium. Now, let's delve into the dynamics of the atmosphere itself and how its stability or lack thereof profoundly influences the development of clouds. Imagine the atmosphere as a layered cake, each layer possessing its own temperature and pressure. The interaction between these layers determines whether the air is stable or unstable, directly impacting the formation and behavior of clouds. Atmospheric stability refers to the atmosphere's tendency to resist or encourage vertical air movement. In a stable atmosphere, a rising air parcel will cool more rapidly than the surrounding air. This cooler parcel becomes denser than its surroundings and sinks back down, suppressing vertical motion and inhibiting cloud development. Think of it like a bouncy ball dropped on a hard surface. It bounces back up due to the resistance of the surface. Stable atmospheres typically result in fair weather with few clouds. Conversely, in an unstable atmosphere, a rising air parcel cools more slowly than the surrounding air. This warmer, less dense parcel continues to rise, further fueling its upward movement. This creates a chain reaction with more and more air rising, leading to significant vertical development of clouds. This is like a ball of clay dropped on a soft surface. It will simply sink in without bouncing back. Unstable atmospheres often result in towering cumulonimbus clouds and stormy weather. The temperature gradient, the rate at which temperature changes with altitude, plays a crucial role in determining atmospheric stability. A steep temperature gradient, meaning a rapid decrease in temperature with height, indicates instability, while a gentle gradient suggests stability. Air pressure also plays a vital role. Lower air pressure at higher altitudes allows rising air parcels to expand and cool more slowly, promoting instability. Conversely, higher pressure at higher altitudes acts to compress rising air, causing it to warm more quickly and thus favoring stability. The interaction between temperature, pressure, and moisture content creates a complex interplay that shapes the very nature of our skies. Understanding these atmospheric dynamics allows meteorologists to predict weather patterns with greater accuracy. It's not merely about isolated pockets of warm and cool air. It's about the overall balance, the delicate equilibrium of forces that dictate whether a gentle cumulus cloud will drift lazily across the sky or a fierce thunderstorm will unleash its power. The seemingly simple act of a cloud forming is, in reality, a complex dance of atmospheric forces, a captivating ballet played out on the vast stage of our atmosphere. The stability of the atmosphere is, therefore, not just a scientific concept. It's the key to unlocking the mysteries of cloud formation and weather prediction. Now, let's turn our attention to a cloud type that's both familiar and visually captivating: the cumulus cloud. Often described as puffy, cotton-like formations, cumulus clouds are a quintessential symbol of fair weather, adding a touch of whimsy to our skies. Their characteristic appearance, with distinct, rounded tops and flat bases, makes them instantly recognizable, even to the untrained eye. These clouds are born from the process of convection, the upward movement of warm, moist air. As warm air near the surface of the Earth absorbs heat, it becomes less dense and begins to rise. As it ascends, it expands and cools, eventually reaching its dew point, the temperature at which the air becomes saturated with water vapor. At this point, the excess water vapor condenses around microscopic particles in the air, known as condensation nuclei, forming visible cloud droplets. These droplets accumulate to form the characteristic fluffy appearance of the cumulus cloud. The flat base of the cumulus cloud marks the altitude at which the rising air reaches its dew point, while the rounded top reflects the continued upward movement of the air, which gradually slows as it encounters cooler, denser air aloft. The size and shape of cumulus clouds vary widely, depending on the strength of the upward air currents and the amount of moisture available. Small, isolated cumulus clouds, often referred to as fair-weather cumulus, are a common sight on sunny days. They typically indicate relatively stable atmospheric conditions, with gentle upward air currents. These clouds are usually bright white, reflecting sunlight effectively, and often appear as scattered puffs against a clear blue sky. Their presence doesn't usually signify any imminent change in weather. Rather, they are an indicator of benign atmospheric conditions. The formation of cumulus clouds is a beautiful demonstration of the interplay between heat, moisture, and atmospheric stability. The rising warm air, the condensation of water vapor, and the eventual slowing of the upward motion all combine to create these iconic cloud formations. They remind us that even seemingly simple weather phenomena are the result of complex atmospheric processes, a delicate balance of forces shaping our world. So, the next time you see a fluffy cumulus cloud drifting across the sky, take a moment to appreciate the intricate science behind its formation, a testament to the ever-changing canvas above us. The seemingly simple cumulus cloud is a miniature marvel of nature, a testament to the beautiful complexity of our atmosphere and a harbinger of a pleasant day ahead. Having explored the cheerful puffiness of cumulus clouds, let's now delve into a different atmospheric spectacle: the stratus clouds. Unlike their cumulus counterparts, stratus clouds present a more subdued, even somber, image. Instead of distinct, individual formations, stratus clouds form a continuous, layered sheet, often blanketing the sky in a uniform gray expanse. These clouds are typically found at low altitudes, hugging the Earth's surface like a vast, gray blanket. Their formation is often associated with stable atmospheric conditions, where a layer of moist air is lifted gently, causing the water vapor to condense into a widespread, uniform layer of cloud droplets. Unlike the vigorous upward currents that create cumulus clouds, stratus clouds develop under conditions of relatively calm, horizontal air movement. The appearance of stratus clouds is often associated with overcast skies, a blanket of gray that diffuses sunlight and casts a muted light on the landscape below. While they might not be as visually striking as some other cloud types, they play a crucial role in the Earth's weather patterns. Stratus clouds can significantly reduce the amount of sunlight reaching the surface, leading to cooler temperatures and a generally damp atmosphere. One of the most common weather phenomena associated with stratus clouds is drizzle. This light, persistent rain, often falling in a fine mist, is formed by the slow condensation and coalescence of tiny water droplets within the cloud layer. Because the droplets are so small, they often evaporate before reaching the ground, leading to that characteristic dampness rather than a heavy downpour. The persistent nature of stratus clouds and their associated drizzle can create a lingering, damp feeling, a sort of atmospheric quietude. The formation of stratus clouds is a fascinating example of how subtle changes in atmospheric conditions can lead to dramatic shifts in weather patterns. The gentle lifting of a moist air mass, the slow condensation of water vapor, and the even distribution of cloud droplets all contribute to the creation of this widespread, layered cloud formation. The next time you find yourself beneath a blanket of stratus clouds, Remember the intricate atmospheric processes at play, shaping the weather and casting a unique, almost melancholic beauty across the landscape. It's a reminder that even the seemingly simple, uniform gray of stratus clouds holds a world of subtle meteorological complexity. And that quiet, persistent drizzle? A testament to the power of even the slightest atmospheric shifts. Now, let's lift our gaze even higher, far above the stratus and cumulus layers, to explore a realm of ethereal beauty, the cirrus clouds. These wispy, feathery formations drift in the upper atmosphere, at altitudes far exceeding those of their lower-lying cousins. Their delicate appearance belies a fascinating composition and a significant role in weather forecasting. Unlike the water droplet-based clouds we've discussed, cirrus clouds are primarily composed of ice crystals. At these high altitudes, temperatures plummet well below freezing, transforming the water vapor into tiny ice particles. These ice crystals, often shaped like delicate needles or thin plates, scatter sunlight in a way that creates their characteristic bright, silky sheen. They can appear almost translucent, their wispy forms etched against the deep blue canvas of the sky. The formation of cirrus clouds is often linked to large-scale atmospheric movements, such as jet streams. These powerful, high-altitude winds transport moisture and ice crystals across vast distances, creating the sweeping, elegant patterns that we observe. Their appearance can vary dramatically, from thin, wispy filaments to more organized, parallel bands, reflecting the complexity of the atmospheric currents that sculpt their forms. Interestingly, the presence of cirrus clouds often serves as an indicator of approaching weather changes. While they themselves don't typically produce precipitation, their formation can signal the presence of an approaching weather system. For example, the appearance of cirrus clouds, followed by an increase in their coverage and density, can often precede the arrival of a warm front, bringing with it the potential for significant changes in temperature and precipitation. In essence, they act as subtle atmospheric messengers, hinting at the larger weather systems unfolding high above. Observing cirrus clouds is not merely an aesthetic experience. It's a window into the dynamic processes of the upper atmosphere. Their delicate beauty and their association with weather changes make them a fascinating subject of study. Their wispy forms, sculpted by powerful winds and composed of ice crystals, remind us of the intricate interplay of forces shaping our weather and influencing our climate. The next time you see these delicate wisps of ice painting the sky, take a moment to appreciate their ethereal beauty and the vital information they convey about the larger atmospheric drama unfolding above. They are, after all, silent storytellers of the sky, whispering tales of atmospheric currents and approaching weather changes. Now, let's turn our attention to the dramatic, the powerful, the rainmakers of the sky, the nimbus clouds. Unlike the delicate cirrus or the puffy cumulus, nimbus clouds are associated with significant precipitation. Their dark, brooding presence often heralding a change in the weather. Their name, derived from the Latin word nimbus, meaning rain cloud, perfectly encapsulates their role in the atmospheric water cycle. Nimbus clouds are not a single type, but rather a broad category encompassing several subtypes, each with its unique characteristics and precipitation patterns. Two of the most prominent are the cumulonimbus and the nimbostratus clouds. Let's explore each of these fascinating cloud formations. Cumulonimbus clouds are perhaps the most dramatic of all. These towering giants, often reaching heights of tens of thousands of feet, are the architects of thunderstorms. Their anvil-shaped tops, spread out like a blacksmith's hammer, are a testament to the powerful updrafts and downdrafts within. These clouds are not only capable of producing heavy downpours but also hail, lightning, and even tornadoes. Their formation is a testament to the immense energy released during atmospheric instability, a powerful display of nature's forces. Their dark, ominous appearance reflects the significant precipitation they hold within. In contrast to the towering cumulonimbus, nimbostratus clouds form a more extensive, layered sheet across the sky. These clouds are typically associated with continuous, widespread rainfall or snowfall, often lasting for hours or even days. Their dark gray appearance and low altitude suggest the heavy precipitation they bring. Unlike cumulonimbus clouds, which are characterized by intense, localized bursts of precipitation, nimbostratus clouds produce a more steady, persistent rain or snow, often obscuring the sun and creating a somber atmospheric mood. The difference between these two types lies largely in their vertical development and the intensity of precipitation they produce. Cumulonimbus clouds are vertically developed, characterized by towering updrafts, while nimbostratus clouds are horizontally extensive, producing widespread and less intense precipitation. Both, however, play a crucial role in the hydrological cycle, redistributing water across the globe. Understanding the differences between these rain-bearing cloud types is crucial for accurate weather forecasting and for appreciating the complex dynamics of atmospheric processes. The next time you see a dark, brooding cloud gathering overhead, remember the powerful forces at play, shaping the weather and sustaining life on Earth. The nimbus clouds, in all their variety, are a constant reminder of the dynamic and vital role clouds play in our world. So far, we've explored various cloud types, their shapes, and the weather they bring. But have you ever considered the vertical dimension of clouds? The sky isn't just a flat canvas. It's a layered atmosphere, and the altitude at which clouds form significantly influences their composition and the weather they produce. Let's embark on a vertical journey through the atmospheric layers, discovering the secrets of cloud altitudes. Meteorologists categorize clouds into three main altitude levels: high, middle, and low. These levels aren't fixed but vary slightly depending on latitude and season. High clouds, typically found above 20,000 feet, exist in the coldest parts of the troposphere, the lowest layer of the atmosphere. The frigid temperatures at these altitudes mean that the clouds are primarily composed of ice crystals. Think of the delicate, wispy cirrus clouds we discussed earlier. Those ethereal, feathery formations are a perfect example of high-altitude cloud formations. Their appearance often signals an approaching weather change, a subtle whisper from the upper atmosphere. Moving lower, to the middle altitude range, between 6,500 and 20,000 feet, we find clouds composed of both water droplets and ice crystals, depending on the temperature. These middle-level clouds, often prefixed with alto, like altocumulus or altostratus, are generally associated with more stable atmospheric conditions than those found at higher or lower levels. Altocumulus clouds often appear as puffy white patches or layers, while altostratus clouds form a more diffuse, grayish layer that can sometimes obscure the sun. Finally, we reach the low-level clouds, typically found below 6,500 feet. Here, temperatures are generally warmer, and the clouds are mostly composed of water droplets. This altitude range is home to the familiar stratus and cumulus clouds we've discussed. These clouds are often closely associated with day-to-day weather changes, bringing drizzle, rain, or simply overcast skies. The low-level clouds are the ones that often directly affect our daily lives, influencing visibility and determining whether we need an umbrella. Understanding cloud altitude is crucial for interpreting weather patterns. The height of a cloud provides valuable clues about its composition, the atmospheric conditions at that altitude, and the type of weather it might produce. The vertical arrangement of clouds, from the icy crystals of high-level cirrus to the water droplets of low-level stratus, paints a vivid picture of the atmosphere's intricate structure and the dynamic processes shaping our weather. It's a journey through the vertical dimensions of the sky, a testament to the beauty and complexity of the natural world above us. The next time you look up at the clouds, remember this vertical journey and appreciate the intricate layering of our atmosphere and the diverse cloud formations it creates. Now that we've explored the vertical stratification of clouds and their diverse forms, let's delve into the fascinating life cycle of a cloud. Imagine a single cloud, not as a static entity, but as a dynamic, ever-changing system, constantly evolving and interacting with its environment. To illustrate this, let's follow the journey of a cumulus cloud, a type readily observable on sunny days. The story begins with the sun's warmth heating the Earth's surface. This warmth, in turn, heats the air directly above it, causing it to rise. This rising air carrying water vapor is known as a thermal. As the thermal ascends, it encounters lower pressure and begins to cool. This cooling process is crucial because it allows the water vapor to reach its dew point, the temperature at which it condenses into tiny water droplets. These droplets cling to microscopic particles in the air, acting as condensation nuclei. This is the birth of our cumulus cloud. Initially, the cloud appears as a small, fluffy puff, a cumulus humulus, a sign of fair weather. However, if the conditions are right, enough moisture and sufficient upward movement of air, the cloud continues to grow. More warm, moist air rises, feeding the cloud's expansion. The cloud becomes taller and more developed, transforming into a cumulus congestus. Its base remains relatively flat, while its top develops a cauliflower-like structure, reaching impressive heights. This stage represents the cloud's adolescence, a period of rapid growth and development. Under certain conditions, particularly with sufficient atmospheric instability and moisture, a cumulus congestus can develop further into a cumulonimbus cloud, a towering thunderhead. This marks the cloud's maturity. Within this massive cloud, strong updrafts and downdrafts create a complex system of air currents, leading to the formation of precipitation, lightning, and thunder. It's a dramatic display of nature's power, a testament to the energy contained within a single cloud. But even the mightiest cumulonimbus cloud cannot sustain itself forever. As the supply of warm, moist air diminishes, the upward movement weakens, and the cloud begins to dissipate. The precipitation falls, and the cloud structure begins to collapse. The cloud slowly shrinks, its once towering form reduced to a smaller, less defined shape. This is the final stage of the cloud's life cycle, a gradual return to the invisible vapor from which it came. This cycle, from the initial formation of a tiny puff to the ultimate dissipation of a mature storm cloud, highlights the dynamic nature of cloud development. Each stage, from humble beginnings to dramatic maturity and eventual decline, is a testament to the constant interplay of atmospheric forces, a captivating dance of moisture, temperature, and air currents, all orchestrated by the sun's energy. It's a reminder of the ephemeral yet powerful presence of these atmospheric wonders. We've witnessed the birth and growth of a cloud, but the story doesn't end there. The magic of weather unfolds as these tiny cloud droplets transform into the precipitation we experience: rain, snow, sleet, or hail. This transformation is a fascinating process involving two primary mechanisms: condensation and coalescence. Condensation, as we've learned, is the initial phase where water vapor in the air changes from its gaseous state to a liquid state. This happens when the air cools to its dew point, and the invisible water vapor condenses onto tiny particles suspended in the air: dust, pollen, sea salt, and even pollutants. These particles act as nuclei, providing a surface for the water molecules to cling to, forming microscopic cloud droplets. Each droplet is incredibly small, far too tiny to fall to the ground as rain. Think of a vast collection of microscopic jewels shimmering in the sky. But these tiny droplets are not static. They are constantly moving, colliding, and interacting within the cloud. Here, coalescence takes center stage. Coalescence is the process by which smaller droplets merge to form larger ones. This process is driven by several factors. Firstly, droplets of different sizes fall at different speeds. Larger droplets, due to their greater weight, fall faster than smaller ones. As they fall, they collide with smaller droplets in their path, merging and growing larger. This process is further enhanced by the presence of updraft and downdraft currents within the cloud. These air currents create a turbulent environment, increasing the frequency of collisions between droplets. The larger the droplets become, the faster they fall, increasing their chances of colliding with even more droplets. This positive feedback loop is crucial for the formation of precipitation-sized droplets. The size a droplet needs to reach before it falls as precipitation depends on several factors, including the cloud's altitude and temperature. In warmer clouds, the droplets grow primarily through coalescence. However, in colder clouds, ice crystals play a vital role. Ice crystals have a greater affinity for water vapor than liquid droplets, so they grow at the expense of the droplets. This process, known as the Bergeron process, is responsible for much of the precipitation we experience in higher altitude clouds. As the droplets continue to grow through coalescence and other processes, they eventually become too heavy to be supported by the upward air currents within the cloud. At this point, they overcome gravity's pull and begin their descent to the Earth's surface, manifesting as rain, snow, or other forms of precipitation. This remarkable transformation, from invisible vapor to a tangible shower, is a constant reminder of the dynamic and intricate processes occurring within our atmosphere. It's a testament to the powerful forces of nature shaping our world, a cycle as old as time itself, a fundamental process driving our planet's weather and climate. Now, let's journey into the enchanting world of snow, a phenomenon as captivating as it is scientifically intricate. Unlike rain, which forms primarily through the coalescence of liquid water droplets, snow's creation unfolds in the frigid embrace of high-altitude clouds, where temperatures plummet far below freezing. Here, the story shifts from liquid to solid, a transformation driven by the elegant dance of ice crystals. Within these icy realms, water vapor doesn't immediately freeze into solid ice. Instead, it often transitions into a supercooled state, liquid water existing below its freezing point. This precarious state is maintained by the lack of nucleation sites, tiny particles that typically trigger the freezing process. However, the presence of ice nuclei, such as dust particles or certain types of bacteria, can initiate the formation of ice crystals. Once an ice crystal forms, it embarks on a remarkable journey of growth. It achieves this primarily through a process called deposition, where water vapor directly transitions from its gaseous state to a solid state, attaching itself to the existing ice crystal. This process is particularly efficient in cold, saturated air, where abundant water vapor is available to fuel the crystal's growth. The shape of these ice crystals is far from uniform. Their intricate designs, often described as snowflakes, are a testament to the complex interplay of temperature, humidity, and air currents within the cloud. Each snowflake is a unique masterpiece, a testament to the subtle variations in these atmospheric conditions. The branching patterns, the delicate symmetry, these are not random occurrences but rather reflections of the precise physical processes at play. As the ice crystals grow, they collide with other ice crystals and supercooled water droplets. These collisions lead to further accretion, adding mass to the crystals and contributing to their complex structures. The larger and heavier these ice crystals become, the more likely they are to fall from the cloud. However, their journey isn't always straightforward. Air currents within the cloud can lift and redistribute the crystals, resulting in a complex dance that can lead to significant accumulations of snow on the ground. The process of snow formation is a beautiful illustration of the power of subtle differences within a system. Tiny variations in temperature and humidity can lead to drastically different snowflake shapes and sizes. This highlights the delicate balance that governs our weather and the intricate beauty inherent in even the most seemingly simple natural phenomena. The next time you witness a snowfall, remember the intricate dance of ice crystals that brought it about, a testament to the elegance and complexity of nature's processes. Now, let's turn our attention to a more dramatic precipitation phenomenon: hail. While snowflakes dance delicately to the earth, hailstones descend with a forceful impact, frozen pellets of ice that can range in size from tiny pebbles to devastatingly large chunks. Their formation is a far more turbulent affair, taking place within the powerful updraft and downdraft currents of strong thunderstorms, those majestic cumulonimbus clouds we discussed earlier. Imagine a thunderstorm, a colossal engine of atmospheric energy. Within its churning heart, powerful updrafts carry water droplets high into the freezing upper reaches of the cloud. Here, these droplets freeze, forming the initial embryonic hailstone, a tiny ice pellet. However, the journey doesn't end there. The hailstone is then caught in a relentless cycle, tossed upwards and downwards by the conflicting air currents. Each upward journey takes it to progressively colder altitudes, where it gathers more supercooled water droplets that freeze onto its surface, adding to its size. Each downward trip exposes the hailstone to warmer layers, potentially causing a thin layer of liquid water to accumulate. As it's once again swept upward, this liquid water refreezes, adding another layer of ice to the growing hailstone. This process of ascent, freezing, descent, and refreezing repeats itself multiple times, building the hailstone layer by layer, like a meticulously crafted onion. Each layer represents a trip through the storm's internal structure, recording the conditions encountered along the way. The resulting hailstone is a fascinating record of the storm's intensity and complexity, its layered structure a testament to its turbulent journey. The size of the hailstone ultimately depends on several factors: the strength of the updrafts, the amount of supercooled water available, and the duration the hailstone spends cycling within the storm. Stronger updrafts can sustain larger hailstones for longer periods, allowing them to grow considerably. Conversely, weaker updrafts may result in smaller hailstones, which fall to the ground more quickly. The formation of large hailstones requires exceptionally powerful thunderstorms, capable of generating intense updrafts and providing ample supercooled water. These storms are often associated with severe weather, capable of producing damaging winds, torrential rainfall, and even tornadoes. Hail, therefore, is not just a fascinating meteorological phenomenon. It's a stark reminder of the destructive potential of nature's raw power. The next time you hear the clatter of hailstones on your roof, take a moment to appreciate the dramatic, violent process that created these frozen messengers from the storm. It's a testament to the dynamic forces at play within our atmosphere, a reminder of the awe-inspiring power and complexity of the weather systems that shape our world. Having explored the fascinating processes behind hail formation, let's broaden our perspective and consider the diverse tapestry of precipitation types that grace, or sometimes batter, our planet. While we've delved into the intricacies of snow and hail, the story of precipitation is far richer and more geographically nuanced than these individual examples might suggest. Rain, the most common form of precipitation, is simply water droplets that have grown sufficiently large to overcome upward air currents and fall to the earth. Its intensity and frequency vary drastically across the globe, influenced by factors like proximity to oceans, altitude, and prevailing wind patterns. Tropical regions, fueled by abundant moisture, often experience heavy, persistent rainfall, while deserts, naturally arid, may go years without a significant downpour. Snow, as we've learned, forms when water vapor deposits directly onto ice crystals, or when supercooled water droplets freeze onto existing ice crystals, building intricate and beautiful snowflakes. This prevalence is largely dictated by temperature. High-altitude regions and high-latitude areas, such as the Arctic and Antarctic, experience consistent snowfall, creating vast snowfields and glaciers. Lower latitudes experience snowfall only during colder months or at higher elevations. Sleet, a less common form of precipitation, is formed when rain falls through a layer of freezing air, transforming into small ice pellets. This requires a specific atmospheric profile, a layer of freezing air above the ground, and warmer air above that layer where the rain initially forms. Sleet is therefore a relatively localized phenomenon, often occurring in mid-latitude regions during transitional seasons. Finally, we have hail, the product of intense thunderstorms, as we've already discussed. Its occurrence is sporadic and geographically concentrated, typically associated with strong convective storms that are more common in certain regions, often those with significant temperature contrasts and abundant atmospheric moisture. The size and intensity of hailstorms vary considerably, ranging from harmless sprinkles to devastatingly destructive events. The global distribution of these precipitation types is a complex interplay of atmospheric dynamics, geographical features, and seasonal variations. Understanding these patterns is crucial not only for predicting weather events but also for managing water resources, agriculture, and mitigating the risks associated with extreme weather phenomena. From the gentle caress of rain to the forceful impact of hail, each form of precipitation plays a vital role in shaping our planet's landscapes, ecosystems, and human societies. The study of precipitation is a continuous journey of discovery, revealing the intricate connections between atmospheric processes and the diverse environments they create. So far, we've explored clouds as individual entities, marveling at their diverse forms and the fascinating processes that create them. But clouds are rarely solitary actors on the atmospheric stage. They are, in fact, integral components of much larger weather systems, playing pivotal roles in shaping the weather patterns we experience daily. Let's now shift our focus to understanding this larger context. One of the most significant ways clouds interact with weather systems is through their association with weather fronts. These are boundaries separating air masses of different temperatures and densities. Warm fronts, where warmer air rises over cooler air, often produce widespread stratiform clouds, like nimbostratus, which can bring persistent rain or snow. The gentle slope of the warm front allows for gradual lifting of the air, leading to a more prolonged period of precipitation. Cold fronts, in contrast, are characterized by a rapid advance of cold air under warmer air. This forceful lifting of warmer air leads to the formation of cumulonimbus clouds, the dramatic thunderheads capable of producing intense showers, thunderstorms, and even hail. The sharp boundary of a cold front often results in a more intense, but shorter-lived, period of precipitation. The dramatic visual contrast between the clear skies behind a cold front and the stormy clouds ahead is a testament to the powerful forces at play. Beyond fronts, clouds are essential elements of larger-scale weather systems like cyclones and anticyclones. Cyclones, or low-pressure systems, are characterized by converging air currents that rise, cool, and condense, forming clouds. The intensity of the cyclone determines the type and amount of cloud cover, ranging from extensive cloud decks associated with larger storm systems to the more localized, yet still significant, cloud formations of smaller cyclones. Cyclones frequently bring unsettled weather, including rain, snow, and strong winds, all intimately connected to the life cycle of the clouds within them. Anticyclones, conversely, are high-pressure systems associated with descending air. This sinking air inhibits cloud formation, resulting in generally clear skies and calm conditions. While clouds are less prominent in anticyclones, their absence contributes to the characteristic stable and often sunny weather associated with these systems. The interplay between these high and low-pressure systems shapes global weather patterns, with clouds acting as both indicators and crucial participants in this dynamic interplay. Understanding the relationship between clouds and these broader weather systems is critical for accurate weather forecasting. By observing cloud patterns, meteorologists can infer the presence and movement of fronts, cyclones, and anticyclones, enabling them to predict the type, intensity, and duration of upcoming weather events. The seemingly simple act of looking up at the clouds, therefore, becomes a powerful tool for understanding the complex and ever-changing atmospheric processes that shape our world. The beauty of the clouds reflects a profound scientific significance, illustrating the interconnectedness of the atmosphere's processes. Having explored the dynamic interplay between clouds and weather systems, let's delve into a more profound and complex aspect of their role: their influence on Earth's climate. Clouds are not simply passive observers in the climate system. They are active participants, wielding a powerful and sometimes paradoxical influence on our planet's temperature. At first glance, it might seem straightforward. Clouds reflect sunlight back into space, thus cooling the Earth. This effect, known as the albedo effect, is particularly significant with highly reflective clouds, such as the bright white stratocumulus clouds that often blanket large areas of the ocean. These clouds act as a natural sunscreen, reducing the amount of solar radiation reaching the Earth's surface and contributing to a cooling effect. The extent of this cooling influence is a subject of ongoing research, as the reflectivity of clouds varies greatly depending on their type, altitude, and thickness. However, the story doesn't end there. Clouds also play a crucial role in warming the Earth. This warming effect arises primarily from the cloud's ability to trap outgoing infrared radiation, otherwise known as the greenhouse effect. Clouds, particularly low-lying clouds like stratus, effectively act as a blanket, preventing heat from escaping into space and thus contributing to a warming effect. This effect is less visually obvious but is a significant contributor to the overall energy balance of the planet. The complexity arises from the fact that these warming and cooling effects are not uniformly distributed across all cloud types. High-altitude, thin clouds, like cirrus, tend to have a net warming effect, as their ability to trap outgoing radiation outweighs their relatively low reflectivity. Low-altitude, thick clouds, on the other hand, often have a net cooling effect due to their high reflectivity and their ability to block incoming solar radiation. This intricate interplay of warming and cooling effects makes predicting the overall impact of clouds on climate change a significant challenge for climate scientists. The precise balance between the warming and cooling effects of clouds is a crucial factor in determining the future trajectory of global temperatures. A better understanding of cloud processes, particularly the way clouds respond to changing atmospheric conditions, is crucial to refine our climate models and improve our ability to predict future climate scenarios. The subtle shifts in cloud cover, seemingly minor changes, can have significant repercussions for global temperatures. Furthermore, human activities are altering cloud properties, adding another layer of complexity to this already intricate puzzle. The emission of aerosols, for instance, can influence cloud formation and reflectivity, leading to both warming and cooling effects, depending on the type and location of the aerosols. Understanding the intricate relationship between clouds, climate, and human activity is crucial for effective climate change mitigation and adaptation strategies. The future of our climate is, in many ways, written in the clouds. And unraveling the secrets held within those wisps and billows is a journey of scientific exploration that continues to this day, with each discovery unveiling a deeper understanding of the delicate balance of our planet's climate. Now, let's unravel a fascinating and crucial aspect of the cloud-climate connection: cloud feedback mechanisms. These mechanisms describe how changes in climate, such as rising temperatures, can influence cloud properties, and how these altered cloud properties, in turn, further affect the climate system. It's a complex dance of cause and effect, a feedback loop that can either amplify or dampen the initial climate change. Imagine a scenario where global temperatures rise. This warming could lead to increased evaporation from the oceans, resulting in more water vapor in the atmosphere. This increased water vapor could then lead to the formation of more clouds. However, the type of clouds formed would significantly impact the overall climate effect. If these are low-level, thick clouds, they would reflect more sunlight back into space, leading to a cooling effect, thus counteracting the initial warming. This is a negative feedback loop. It dampens the initial change. But the story isn't always so simple. If the increased water vapor leads to the formation of high-level, thin clouds, these clouds would primarily trap outgoing heat radiation, resulting in a warming effect. This would amplify the initial warming, creating a positive feedback loop. The implications are profound, as positive feedback loops can accelerate climate change, making it more challenging to manage. The uncertainty surrounding cloud feedback mechanisms is a major source of uncertainty in climate models. Different models incorporate different assumptions about how clouds will respond to changing climate conditions, leading to a range of potential future climate scenarios. The challenge lies in the complexity of cloud behavior and the numerous factors influencing cloud formation, lifetime, and properties. For example, the effect of clouds on precipitation patterns is a crucial element in these feedback loops. Changes in cloud cover can alter rainfall distribution, impacting agricultural productivity, water resources, and ecosystems globally. Similarly, the impact of clouds on the hydrological cycle, the continuous movement of water on, above, and below the surface of the Earth, is a vital consideration. Changes in cloud patterns can disrupt this cycle, leading to droughts in some regions and floods in others. Furthermore, the interaction between clouds and aerosols, tiny particles suspended in the atmosphere, adds another layer of complexity. Aerosols can influence cloud formation by acting as cloud condensation nuclei, the tiny particles around which water vapor condenses to form cloud droplets. Human activities, such as the burning of fossil fuels, release large quantities of aerosols into the atmosphere, impacting cloud properties and their feedback effects on climate. In conclusion, understanding cloud feedback mechanisms is paramount for accurately predicting future climate change. The delicate balance between these various feedback loops determines whether climate change will proceed at a slower or faster rate. The ongoing research into these mechanisms is crucial for developing effective strategies to mitigate the effects of climate change and to ensure a sustainable future for our planet. The clouds, in their silent, ever-changing majesty, hold vital clues to Earth's climate destiny. Let's delve into the intricate dance between clouds and the Earth's energy budget, the balance between incoming solar radiation and outgoing terrestrial radiation. This delicate balance governs our planet's temperature, and clouds play a surprisingly significant, an often contradictory role. Imagine the sun's radiant energy, a ceaseless torrent of light and heat bombarding our planet. A significant portion of this incoming solar radiation is reflected back into space. Clouds, depending on their type and altitude, act as powerful reflectors, sending a substantial amount of solar energy back into the cosmos before it can warm the Earth's surface. This reflective property, known as albedo, is particularly pronounced with low-lying, thick clouds like stratocumulus. They act like giant mirrors, deflecting sunlight and contributing to a net cooling effect on the planet. However, the story doesn't end there. Clouds also interact with terrestrial radiation, the infrared energy emitted by the Earth's surface after being warmed by the sun. Unlike solar radiation, which is primarily shortwave radiation, terrestrial radiation is longwave radiation. High-altitude, thin clouds such as cirrus clouds are remarkably efficient at trapping this outgoing longwave radiation, preventing it from escaping into space. This trapping effect acts like a blanket, warming the Earth's surface and the lower atmosphere. This greenhouse effect, while crucial for maintaining habitable temperatures, can be amplified by increased cloud cover, leading to a warming effect. The net impact of clouds on the Earth's energy budget is therefore a complex interplay of these competing effects. The balance between the cooling effect of reflected solar radiation and the warming effect of trapped terrestrial radiation depends on several factors, including cloud type, altitude, cloud cover, and the amount of water vapor within the clouds. It's a dynamic and ever-shifting equilibrium. Scientists employ sophisticated climate models to simulate the effects of clouds on the Earth's energy budget, but significant uncertainties remain. The complexity of cloud processes and the limitations of current technology make precise predictions challenging. Discrepancies in how different climate models represent clouds contribute to the range of possible future climate scenarios. Further research into cloud physics and their interactions with other atmospheric components is crucial for improving the accuracy of these models and refining our understanding of climate change. The impact of clouds on regional and local climates is equally significant. Variations in cloud cover can lead to substantial temperature differences, influencing rainfall patterns, agricultural yields, and even the intensity of extreme weather events. Understanding the role of clouds in these local variations is critical for effective weather forecasting and climate adaptation strategies. The seemingly simple wisp of cloud, therefore, holds within it a complex story of energy transfer, atmospheric dynamics, and profound implications for our planet's climate. The continued study of these fascinating formations is essential for our understanding of the intricate mechanisms shaping our world. How do we, from our vantage point on Earth, truly understand these celestial wonders, these ephemeral sculptures of the atmosphere? The answer lies in a fascinating array of tools and techniques employed by meteorologists to observe and study clouds, providing us with a wealth of data that unravels their mysteries. One of the most powerful tools in our arsenal is the Hubble weather balloon. These seemingly simple instruments, filled with helium and carrying a package of sensors, ascend high into the atmosphere, providing real-time measurements of temperature, humidity, pressure, and wind speed. These vital measurements give us a detailed profile of the atmospheric conditions that influence cloud formation and development, painting a picture of the invisible forces at play. The data collected allows scientists to track the vertical structure of clouds, revealing their internal dynamics and providing crucial information for weather forecasting. Next, we have the all-seeing eye of satellites. Orbiting high above the Earth, these technological marvels provide a global perspective on cloud cover, revealing patterns and distributions that would otherwise remain hidden. Equipped with sophisticated sensors, satellites capture images in various wavelengths of light, allowing us to see not only the visible features of clouds, but also their thermal properties and their composition, revealing details about their water content and the presence of ice crystals. This broad overview is essential for understanding large-scale weather systems and their influence on climate. Finally, we turn to weather radar, a sophisticated technology that uses radio waves to detect and track precipitation within clouds. By emitting pulses of radio waves and measuring the time it takes for the echoes to return, radar systems can determine the location, intensity, and movement of precipitation, providing crucial information for severe weather warnings and short-term forecasting. Furthermore, advanced radar techniques can also provide insights into the internal structure of clouds, giving meteorologists a three-dimensional view of their development and evolution. The data collected by radar is invaluable for understanding the processes that lead to heavy rainfall, hailstorms, and other severe weather events. The combined use of these technologies, weather balloons, satellites, and radar, provides a comprehensive and multifaceted approach to cloud observation. Each technique offers a unique perspective, allowing scientists to build a detailed and nuanced understanding of these atmospheric phenomena. From the intimate details revealed by weather balloons to the global perspective provided by satellites, and the dynamic insights provided by radar, this collection of tools allows us to delve into the intricacies of clouds, revealing their secrets and enhancing our ability to predict and understand the weather. It's a testament to human ingenuity, allowing us to better understand the ever-changing canvas above. Imagine peering into a crystal ball, not to see the future of romance or fortune, but to glimpse the weather ahead. That's essentially what meteorologists do, though their crystal ball is a complex interplay of data, models, and a deep understanding of atmospheric dynamics, particularly the behavior of clouds. Cloud forecasting isn't just about predicting whether it will rain or shine. It's about understanding the intricate dance of atmospheric forces that shape our weather. The observations gathered by weather balloons, satellites, and radar, those diligent eyes in the sky, are the raw ingredients for our weather predictions. These observations provide a snapshot of the current state of the atmosphere, including temperature, humidity, pressure, and wind speed, alongside detailed images of cloud formations. But simply knowing the current conditions isn't enough. We need to understand how these conditions will evolve over time. This is where the science of cloud dynamics comes into play. Understanding how clouds form, grow, and dissipate is crucial to forecasting their impact on the weather. For instance, the type of cloud, wispy cirrus, towering cumulonimbus, or layered stratus, indicates different atmospheric conditions and potential weather outcomes. The movement and evolution of these clouds, as tracked by radar and satellites, reveal the direction and speed of air masses, helping predict the arrival of rain, snow, or even severe weather. Meteorologists use sophisticated computer models to simulate the atmosphere, incorporating the observed data and our understanding of cloud dynamics. These models are incredibly complex, accounting for numerous variables and interactions, and they constantly refine their predictions as new data becomes available. The accuracy of these predictions depends heavily on the quality and quantity of the input data, particularly the detailed observations of clouds. However, cloud forecasting is not an exact science. Clouds are inherently complex and chaotic systems, and small changes in initial conditions can lead to significant variations in their behavior. This is why weather forecasts often come with a degree of uncertainty, particularly when dealing with severe weather events. Despite these challenges, advances in technology and our understanding of cloud dynamics are continually improving the accuracy and reliability of weather forecasts, allowing us to better prepare for the ever-changing weather patterns of our planet. The ability to predict the future, even just a few hours or days ahead, is a testament to the power of scientific observation and the ongoing quest to understand the whispers of the sky. Picture this: a colossal airliner, a marvel of engineering, soaring through the vast expanse of the sky. Its journey, seemingly effortless, is intricately interwoven with the unseen forces of the atmosphere, particularly the often overlooked world of clouds. For pilots and air traffic controllers, understanding clouds isn't just a matter of appreciating their beauty. It's a critical element of ensuring safe and efficient air travel. Clouds are far more than just picturesque formations. They represent dynamic atmospheric phenomena that can significantly impact flight operations. From gentle turbulence to severe thunderstorms, the impact of clouds on aviation safety is profound. Imagine the challenges posed by navigating through a dense cumulonimbus cloud, a towering behemoth capable of generating intense turbulence, hail, and even lightning strikes. These aren't just inconveniences. They represent serious threats to flight safety. Pilots rely heavily on weather reports and forecasts to plan their routes, choosing altitudes and trajectories that avoid potentially hazardous weather conditions. Understanding the types of clouds present, their vertical extent, and their associated weather phenomena is crucial for making informed decisions. For example, the presence of towering cumulonimbus clouds indicates the potential for severe turbulence, heavy precipitation, and lightning, prompting pilots to reroute or delay flights. Furthermore, visibility is a paramount concern for aviation safety. Dense clouds can drastically reduce visibility, making it difficult for pilots to navigate and land safely. This is why pilots use specialized instruments and rely on weather radar to monitor cloud formations and adjust their flight plans accordingly. In low visibility conditions, instrument landing systems, ILS, guide aircraft safely to the runway, relying on radio signals and ground-based equipment. These systems, however, require clear airspace around the airport, making understanding cloud cover crucial for safe landings. Beyond immediate safety concerns, clouds also play a role in flight planning in less dramatic ways. High-altitude cirrus clouds, while usually posing minimal threat to flight, can impact the efficiency of jet engines by reducing the density of the air. This subtle yet significant factor is taken into consideration when planning flight routes and fuel consumption. Even seemingly innocuous clouds can affect air travel. The planning and execution of every flight are intimately linked to a thorough understanding of cloud behavior. The seemingly simple act of flying an airplane is a testament to the sophisticated coordination between human skill, technological advancement, and a deep understanding of the atmospheric environment, especially the ever-changing canvas of clouds. From the earliest cave paintings to the most modern digital art, clouds have captivated the human imagination, serving as both a subject of awe and a symbol of profound emotions. Their ephemeral nature, their constant transformation, and their inherent mystery have inspired artists and writers for millennia. Let's embark on a journey through time, exploring how clouds have been depicted in art and literature, reflecting humanity's enduring fascination with these celestial wonders. Consider the Romantic painters of the 19th century, masters of capturing the sublime power of nature. Artists like Caspar David Friedrich and J. M. W. Turner masterfully rendered clouds, not just as atmospheric elements, but as potent symbols of the emotional and spiritual landscape. Their canvases are filled with dramatic skies, clouds swirling and churning, mirroring the turbulent emotions of the human heart. These weren't mere depictions. They were expressions of the sublime, the awe-inspiring power of nature that both terrifies and captivates. Moving beyond the Romantic era, Impressionist painters like Claude Monet and Camille Pissarro captured the fleeting beauty of clouds in their vibrant landscapes. Their interest lay not in representing clouds with precise detail, but in capturing the ephemeral play of light and shadow, the ever-shifting textures and colors of the sky. Their paintings, often focused on atmospheric effects, highlight the transient nature of clouds, their constant dance across the canvas of the sky. In literature, clouds have served as metaphors for a wide range of human experiences, from Shakespeare's dramatic storm clouds signifying impending doom to the serene, idyllic clouds of pastoral poetry. These celestial formations have mirrored the emotional spectrum of human life. Think of the weight of dark clouds looming over a tragic tale, or the lightness and fluffiness of clouds contrasting with the melancholy of a somber narrative. Clouds in literature are rarely just clouds. They are symbols, metaphors, and powerful narrative devices. Clouds have also found their way into mythology and folklore. In many cultures, clouds are associated with deities and supernatural beings, representing the power and mystery of the heavens. From the rain clouds bringing life-giving water to the storm clouds signifying the wrath of the gods, clouds have held cultural significance across different societies. These narratives, passed down through generations, reveal a deep connection between humanity and the atmospheric phenomena that shape our world. The artistic and literary depictions of clouds reveal more than just aesthetic appreciation. They showcase humanity's profound connection with the natural world. Through centuries of artistic expression, the cloud has become a powerful symbol, a reflection of our emotions, our beliefs, and our ever-evolving understanding of the universe. The way we portray clouds in art and literature mirrors our own journey of understanding the world around us, a testament to the enduring power of these atmospheric wonders. Have you ever looked up at the sky, expecting a calm, sunny day, only to be greeted by the unexpected drama of a sudden thunderstorm? The beauty of weather lies, in part, in its inherent unpredictability. While meteorologists strive to forecast with increasing accuracy, the atmosphere remains a complex system, prone to surprising shifts and dramatic displays. Let's delve into the captivating unpredictability of cloud formations and their associated weather phenomena. The seemingly innocent cumulus cloud, a fluffy white puff against a blue sky, can rapidly transform into a towering cumulonimbus, a storm cloud capable of unleashing torrential rain, hail, and even tornadoes. This dramatic metamorphosis highlights the volatile nature of atmospheric processes, where subtle shifts in temperature, humidity, and wind patterns can trigger a cascade of events, leading to spectacular, and sometimes hazardous, weather phenomena. Consider the mesmerizing beauty of a lenticular cloud, resembling a UFO hovering over a mountain peak. These lens-shaped clouds are formed by air flowing over mountains, creating wave-like patterns in the atmosphere. Their smooth, otherworldly appearance belies the powerful atmospheric forces at play, a reminder that even the most visually stunning cloud formations are the result of complex interactions within the atmosphere. Then there are the iridescent clouds, shimmering with vibrant colors like an oil slick on water. These fleeting displays are caused by the diffraction of sunlight by tiny ice crystals or water droplets within the clouds, creating a spectacle of color that can leave even the most seasoned weather observer in awe. Their short-lived nature only adds to their allure, a reminder of the ephemeral beauty that nature occasionally bestows upon us. The unpredictable nature of weather extends beyond the visual spectacle. Unexpected changes in wind speed and direction can transform a gentle rain into a powerful downpour, or a light snow into a blizzard. These shifts can have significant impacts on our daily lives, disrupting travel plans, affecting agricultural yields, and even posing safety risks. Yet, this unpredictability is also what makes weather so fascinating. It's the element of surprise, the unexpected turn of events, that keeps us captivated by the ever-changing canvas above. The beauty of unexpected weather lies in its power to remind us of the awesome forces shaping our world, forces that we are only beginning to fully understand. From the gentle caress of a summer rain to the ferocious power of a hurricane, weather reminds us of both the fragility and the resilience of life on Earth. It is a constant reminder of the intricate dance between the atmosphere and the land, a dance that continues to unfold day after day, in a breathtaking display of natural artistry. The next time you look up at the sky, remember this inherent unpredictability, for it is in this dynamism that the true beauty and wonder of weather truly resides. Clouds, fleeting masterpieces sculpted across the vast canvas of the sky. Their ephemeral nature, their constant transformation, presents a unique challenge and irresistible allure to photographers worldwide. Capturing the essence of a cloud, its texture, its light, its fleeting mood, is an art form in itself, demanding patience, skill, and a keen eye for detail. The beauty of cloud photography lies in its ability to capture a moment in time, a transient beauty that will never be replicated. A single cloud can shift its form in mere seconds, its texture altering with the changing light, its color deepening or fading with the passage of the sun. To capture this ephemeral beauty requires a deep understanding of light and shadow, of composition and perspective. Photographers often employ various techniques to capture the essence of the cloud. The golden hour, that magical time just after sunrise or before sunset, provides a soft, warm light that enhances the cloud's texture and reveals its subtle variations in color and density. Conversely, dramatic storm clouds, often lit by the intense light of a setting sun, offer an entirely different aesthetic, filled with dramatic contrasts and powerful visual impact. The choice of equipment also plays a significant role. Wide-angle lenses are frequently used to capture the vast expanse of the sky, showcasing the grandeur of a panoramic cloud formation. Telephoto lenses, on the other hand, allow for a closer look at the intricate details of individual clouds, revealing their textures and patterns. Polarizing filters can help reduce glare and enhance color saturation, while graduated neutral density filters can balance the exposure between the bright sky and a darker foreground. But the best equipment in the world is useless without a keen eye and a patient spirit. Cloud photography often demands hours of waiting, observing, and anticipating the perfect moment. The photographer must become attuned to the subtleties of atmospheric changes, anticipating shifts in light and cloud formations, ready to capture the fleeting beauty as it unfolds. The rewards, however, are immense. A well-executed cloud photograph can evoke a sense of awe, wonder, and tranquility. It can capture the majesty of nature, the beauty of the unpredictable, and the ephemeral nature of time itself. It can be a powerful reminder of the beauty that surrounds us, often overlooked in the rush of daily life. So, the next time you see a stunning cloud formation, take a moment to appreciate its beauty, and perhaps even consider the challenge and the reward of attempting to capture its fleeting essence through the lens of your camera. The sky, after all, is an ever-changing gallery of natural art, waiting to be discovered and documented. Look up, gaze at the ever-shifting canvas above. For millennia, humans have not simply observed clouds. We've woven them into the very fabric of our stories, our beliefs, our understanding of the world. Clouds, in their majestic, ever-changing forms, have become characters in the grand narrative of human mythology. Across cultures, clouds have been imbued with meaning, often reflecting the anxieties and aspirations of the societies that observed them. In ancient Greece, the gods themselves were believed to reside among the clouds, their moods reflected in the weather below. Zeus, the king of the gods, wielded thunder and lightning, his power manifested in the dramatic spectacle of a stormy sky. The gentle rain, on the other hand, was often attributed to the benevolent actions of other deities, representing fertility and abundance. Native American cultures often viewed clouds as the breath of powerful spirits, their movements dictating the rhythms of life on Earth. Certain cloud formations were interpreted as signs, omens, or messages from the spirit world. The dance of clouds across the sky was a reflection of the cosmic forces shaping their lives, a source of both awe and apprehension. In Norse mythology, the clouds played a crucial role in the creation of the world. Ymir, a primordial giant, was slain, and his body formed the earth, the sky, and the clouds. The clouds themselves were often seen as the dwelling place of the gods, a celestial realm of power and mystery. Across Asia, clouds were often associated with dragons, powerful mythical creatures that controlled the weather and brought both blessings and destruction. In Chinese mythology, the dragon's breath manifested as rain, representing the life-giving force of nature. However, its wrath could also unleash devastating storms, highlighting the dual nature of clouds, both a source of sustenance and a potential force of destruction. Even in modern times, clouds continue to inspire our imagination. We see faces in the clouds, we tell stories about their shapes, we project our own emotions and experiences onto their ever-changing forms. This enduring fascination speaks volumes about our deep connection to the natural world and the inherent human need to find meaning and narrative in the phenomena that surround us. The clouds, in their silent, ethereal beauty, continue to whisper tales from the dawn of time, reminding us of the rich tapestry of myths and legends that have shaped our understanding of the world and our place within it. Their ethereal presence is a constant reminder of the power of storytelling and the enduring human capacity for wonder and imagination. We've journeyed through the ethereal beauty of clouds, explored their scientific intricacies, and delved into the rich tapestry of myths and legends they inspire. But our story isn't complete without acknowledging a crucial and often unsettling aspect: the impact of humanity on these magnificent atmospheric phenomena. The delicate balance of cloud formation and precipitation, a process honed over millennia, is now facing unprecedented challenges. Human activities, primarily the burning of fossil fuels and deforestation, are releasing vast quantities of pollutants into the atmosphere. These pollutants, including aerosols and greenhouse gases, act as tiny particles around which water vapor condenses, significantly altering the process of cloud formation. Increased aerosols, for example, can lead to brighter, more reflective clouds, potentially cooling the planet by reflecting more sunlight back into space. However, this effect is complex and not fully understood. Some aerosols can also lead to the formation of smaller, less efficient cloud droplets, hindering precipitation and potentially leading to droughts in some regions. The increase in greenhouse gases, on the other hand, is warming the planet, leading to a more complex and unpredictable weather pattern. Warmer temperatures cause increased evaporation, leading to more water vapor in the atmosphere, the fundamental building block of clouds. This increased water vapor can fuel more intense precipitation events, resulting in more frequent and severe floods and storms. But the impact goes beyond simply changing the amount of precipitation. Changes in atmospheric circulation patterns, driven by climate change, are altering the distribution of clouds across the globe. Some regions may experience more frequent cloud cover, leading to changes in temperature and sunlight availability. Other regions may experience less cloud cover, leading to increased heat waves and droughts. These shifts have profound implications for agriculture, water resources, and ecosystems worldwide. The consequences are far-reaching. Changes in cloud cover can disrupt agricultural yields, impacting food security globally. Altered precipitation patterns can exacerbate water scarcity in already arid regions, leading to conflicts over resources and displacement of populations. Extreme weather events, fueled by changes in cloud formation and precipitation, pose a significant threat to human lives and infrastructure. The intricate dance between clouds and climate is a delicate one, easily disrupted by human actions. Understanding this complex interaction is crucial if we are to mitigate the negative impacts of climate change and protect the delicate balance of Earth's climate system. The future of our clouds, and indeed our planet, depends on our collective action and our commitment to a sustainable future. The whispers of the sky are calling for change, urging us to consider the profound consequences of our impact on this wondrous natural phenomenon. As we conclude our exploration of the wonders of clouds, let's shift our focus from the scientific and historical to the deeply personal. We've delved into the physics, the history, and the impact of these celestial formations. But perhaps the most rewarding aspect of understanding clouds lies in simply appreciating their beauty and the profound connection they offer to the natural world. Take a moment, close your eyes, breathe deeply. Now imagine yourself looking up. What do you see? A vast expanse of blue, perhaps punctuated by fleeting wisps of white, or maybe a dramatic, brooding sky, heavy with the promise of rain. Each cloud formation, each subtle shift in color and texture, is a unique masterpiece painted by the forces of nature. We often rush through our days, heads down, lost in the whirlwind of our busy lives. We rarely pause to truly appreciate the breathtaking spectacle unfolding above us. But if we take the time to look up, to truly observe, we discover a world of wonder, a captivating show that unfolds daily, free for all to witness. Notice the delicate tracery of cirrus clouds, high in the stratosphere, their feathery tendrils hinting at the winds that sculpt their forms. Marvel at the fluffy cumulus clouds, piled high like cotton balls, their shapes constantly changing, evolving in the gentle currents of air. Feel the weight of the ominous nimbostratus, pregnant with rain, their dark, brooding presence a reminder of the power of nature. Each cloud is a story, a testament to the dynamic processes shaping our atmosphere. They are fleeting works of art, ephemeral masterpieces that appear and disappear, constantly transforming, never quite the same from one moment to the next. Their ever-changing forms reflect the ever-changing moods of the atmosphere, a testament to the constant flux and transformation that is the essence of nature. Take your time. Let the clouds inspire you. Let them fill you with a sense of awe and wonder. Their beauty is not simply aesthetic. It's a profound connection to the larger system of which we are a part. By observing clouds, we are connecting with the weather, with the climate, with the very essence of our planet. Find a quiet spot, lie back on the grass, and simply let your gaze drift upwards. Notice the interplay of light and shadow, the subtle variations in color and texture. Let the clouds transport you to dreamland, to faraway places, to moments of peace and tranquility. Let them inspire you to slow down, to appreciate the simple beauty of the natural world, and to deepen your connection with the planet we all call home. The ever-changing canvas above is a constant reminder of the wonder and beauty that surrounds us, waiting to be discovered, waiting to be appreciated. So look up and let the clouds inspire you. Let them remind you of the beauty, the power, and the profound interconnectedness of our world. And remember, the sky is always watching, always changing, always whispering its secrets to those who take the time to listen. Now, let's turn our attention to a wonderfully simple yet deeply rewarding activity: cloud watching. Forget complicated equipment or demanding schedules. All you need is a clear sky, a comfortable spot, and a curious mind. Cloud watching is a gateway to a world of wonder, a peaceful pastime that can be both relaxing and surprisingly educational. Find a quiet place, whether it's a park bench, a sun-drenched meadow, or even your own backyard. Lie back, relax, and let your gaze drift upwards. Allow your mind to wander, letting the ever-shifting forms of the clouds inspire your imagination. What shapes do you see? Animals? Faces? Objects? The possibilities are endless. This simple act of observation can be surprisingly calming. The slow, graceful movement of the clouds can have a meditative effect, helping to quiet the mind and ease the stresses of daily life. It's a chance to disconnect from the digital world and reconnect with the natural rhythms of the planet. But cloud watching isn't just about relaxation. It's also a fantastic opportunity to learn. As you observe the clouds, try to identify different types. Are they fluffy cumulus clouds, hinting at fair weather? Or are they darker, more ominous nimbostratus, suggesting the possibility of rain? Learning to distinguish between cloud types can enhance your understanding of meteorology and weather patterns. There are many resources available to help you on your cloud watching journey. Numerous websites and apps offer detailed information about cloud identification and classification. Books on meteorology and cloud formation can provide a deeper understanding of the scientific processes that shape these celestial formations. Even a simple guide to cloud types can be a valuable tool in enhancing your cloud watching experience. Don't be afraid to experiment. Try cloud watching at different times of day and in different weather conditions. Notice how the clouds change shape and form throughout the day, influenced by sunlight, wind, and temperature. Document your observations, take photos, keep a journal, or simply commit the shapes and formations to memory. Cloud watching is an accessible activity, suitable for all ages and skill levels. It's a perfect way to spend time with family and friends, sharing observations and fostering a sense of wonder and appreciation for the natural world. So, the next time the sky is clear, take a moment to look up, to relax, to learn, and to appreciate the simple pleasure of cloud watching. Let the clouds inspire you, surprise you, and reconnect you with the beauty and wonder of the world around you. It's a journey of discovery waiting for you, right above your head. We've explored the beauty and science of clouds, from their formation to their impact on our weather. But did you know you can actively contribute to our understanding of these magnificent atmospheric phenomena? Enter the fascinating world of citizen science, where everyday individuals like you can play a vital role in scientific discovery. Citizen science initiatives related to clouds offer a unique opportunity to participate in real-world research. These projects often involve observing, recording, and submitting data about clouds, contributing to a larger dataset that scientists use to improve weather forecasting, climate modeling, and our overall comprehension of cloud behavior. It's a powerful way to combine your passion for nature with a meaningful contribution to scientific advancement. Imagine contributing to a global network of cloud watchers, your observations forming part of a vast, collaborative effort to understand the intricate dynamics of our atmosphere. Through various platforms and apps, you can easily document cloud types, their formations, and associated weather conditions. This data, when aggregated, provides scientists with a much broader and more detailed picture than could ever be achieved through traditional methods alone. Participating in citizen science projects related to clouds is surprisingly simple. Many initiatives provide user-friendly interfaces and clear instructions on how to make observations and submit your data. Some projects might involve taking photographs of clouds, noting their characteristics, and providing information about the time and location of your observation. Others might require you to participate in more structured data collection using specific methodologies and tools. The impact of citizen science contributions is profound. Scientists rely on this valuable data to refine their models, improve the accuracy of weather forecasts, and gain a deeper understanding of climate change's impact on cloud patterns and precipitation. Your individual observations, combined with thousands of others, contribute to a more complete and accurate representation of cloud behavior across different regions and climates. Furthermore, participating in these initiatives offers a unique opportunity to learn more about meteorology, cloud physics, and the scientific process itself. It's a chance to engage with the scientific community, connect with fellow enthusiasts, and contribute directly to a greater understanding of our planet's complex atmospheric systems. So, consider joining a citizen science project related to clouds. It's a fascinating way to combine your love for nature with a meaningful contribution to scientific knowledge. Your participation matters, and it's easier than you might think to get involved. Explore the resources available online and discover how you can contribute to the ever-expanding knowledge of our fascinating skies. As we've journeyed through the captivating world of clouds, from their whimsical formations to their profound impact on our planet, we arrive at a point of both wonder and anticipation. The future of cloud research. The quest to understand these celestial wonders continues, driven by an ever-growing need for accurate weather forecasting and sophisticated climate modeling. Current research focuses on several key areas. Scientists are employing advanced technologies, such as sophisticated satellite imagery and high-resolution radar systems, to capture detailed data on cloud formations, their movements, and their interactions with atmospheric conditions. This data allows for a more nuanced understanding of cloud dynamics, leading to improved weather prediction models. One exciting frontier is the development of more accurate climate models. Clouds play a complex role in regulating the Earth's temperature, reflecting sunlight back into space while simultaneously trapping heat. Understanding these opposing effects is crucial for predicting future climate scenarios. Researchers are refining their models to better incorporate the complexities of cloud behavior, leading to more accurate projections of future climate change. Another area of intense research is the impact of human activities on cloud formation and precipitation patterns. Scientists are investigating how pollution, deforestation, and other human-induced changes to the atmosphere affect cloud behavior and, consequently, weather patterns. This research is critical for understanding and mitigating the impact of climate change on weather systems and water resources. The development of artificial intelligence and machine learning is revolutionizing cloud research. These technologies are being used to analyze vast datasets of cloud observations, identify patterns and anomalies, and improve the accuracy of weather forecasting and climate models. AI-powered systems can process and interpret data at a speed and scale that would be impossible for humans alone, leading to significant advancements in our understanding of clouds. Furthermore, ongoing research focuses on improving our ability to predict extreme weather events, such as hurricanes, floods, and droughts. These events often involve complex interactions between clouds and other atmospheric phenomena, making accurate prediction challenging. Advanced research techniques, coupled with improved data collection and analysis, are helping scientists develop more effective early warning systems, potentially saving lives and minimizing damage. The future of cloud research holds immense promise, with ongoing advancements potentially transforming our ability to predict and respond to weather events. By continuing to unravel the mysteries of clouds, scientists will be better equipped to address the challenges of climate change and build a more resilient and sustainable future. The journey into the heart of cloud science continues, promising exciting discoveries and a deeper understanding of our ever-changing world. As we gaze upward at the ever-shifting canvas of the sky, it's easy to lose ourselves in the beauty of the clouds. But beyond their aesthetic appeal lies a profound significance, one deeply intertwined with the future of our planet. Understanding clouds isn't merely an academic pursuit. It's a critical component in addressing the pressing environmental challenges of our time. The role of clouds in regulating Earth's temperature is complex and multifaceted. They act as both a shield and a blanket, reflecting sunlight back into space while simultaneously trapping heat radiated from the Earth's surface. The delicate balance between these opposing forces is crucial for maintaining a stable climate. However, human activities, particularly the release of greenhouse gases, are disrupting this balance, leading to global warming and a cascade of environmental consequences. Accurate climate modeling relies heavily on our understanding of cloud behavior. The intricate interactions between clouds, aerosols, and other atmospheric components are still not fully understood, creating significant uncertainties in climate predictions. Improving our ability to model cloud behavior is essential for refining climate projections and developing effective mitigation strategies. The more precise our understanding, the more effective our responses can be. Climate change is not just an abstract concept. It's already impacting weather patterns around the globe, leading to more frequent and intense extreme weather events. These events, from devastating hurricanes to prolonged droughts, pose significant threats to human populations and ecosystems. Advanced cloud research is crucial for developing early warning systems and improving our ability to predict and mitigate the impacts of these events. Furthermore, clouds play a vital role in the global water cycle, influencing precipitation patterns and the availability of freshwater resources. Changes in cloud behavior due to climate change can have profound consequences for agriculture, water security, and human livelihoods. Understanding these changes is crucial for adapting to a changing climate and ensuring the sustainability of our water resources. In conclusion, the seemingly ethereal world of clouds holds the key to understanding and addressing some of the most pressing challenges facing our planet. By continuing to invest in research, refining our models, and collaborating across disciplines, we can unlock the secrets held within these celestial formations and build a more sustainable and resilient future. The future of our planet is, in many ways, written in the clouds. Let us learn to read that writing with both care and urgency. As our journey through the world of clouds draws to a close, let us pause for a moment and reflect on the profound beauty and enduring mystery they hold. These ephemeral sculptures, sculpted by the wind and painted by the sun, are a constant reminder of the dynamic forces shaping our planet. Each cloud, from the wispiest cirrus to the most imposing cumulonimbus, is a testament to the power and artistry of nature. Look up now wherever you are. Observe the subtle shifts in light and shadow, the ever-changing patterns etched across the sky. These are not merely passive decorations. They are active participants in the grand drama of Earth's weather. They are the breath of the planet, the vehicles of its water cycle, the architects of its climate. The mystery of clouds continues to fascinate scientists and poets alike. Their complex interactions with sunlight, radiation, and atmospheric aerosols remain a source of ongoing research and discovery. Yet, even with advanced technology and sophisticated models, there is still much we do not know. This inherent mystery adds to their allure, inviting us to look closer, to question, to wonder. The clouds are a constant source of inspiration, a muse for artists, writers, and musicians. They have been woven into myths and legends across cultures for millennia, symbolizing everything from divine power to fleeting moments of beauty. They are a source of comfort, a reminder of the vastness of the universe, and a gentle invitation to contemplation. But beyond their aesthetic appeal, clouds hold a deeper significance. Their behavior directly impacts our lives, influencing our weather, our food production, and our water resources. Understanding them is crucial for navigating the challenges of a changing climate and ensuring a sustainable future for generations to come. So, as you go about your day, take a moment to look up at the sky, appreciate the beauty and complexity of the clouds, and remember the vital role they play in our world. Let their ever-changing forms inspire awe, curiosity, and a deeper appreciation for the intricate balance of nature. The sky is not just above us. It's a part of us, a constant reminder of the wonders and mysteries that surround us. And the clouds, those fleeting masterpieces, are a vital thread in the tapestry of our world. Now, let's bring our exploration of clouds closer to home. I invite you to take a moment, right now, to look out at your own local skies. What do you see? Are fluffy cumulus clouds scattered across a brilliant blue canvas, hinting at a pleasant afternoon? Or perhaps towering cumulonimbus clouds loom on the horizon, promising a dramatic thunderstorm? The clouds above you are telling a story specific to your location. Consider your geographical location. Are you near a coast, where maritime air masses might bring frequent low-lying stratus clouds and gentle sea breezes? Or are you inland, perhaps in a mountainous region where orographic lift creates unique cloud formations and dramatic weather patterns? The landscape itself plays a significant role in shaping the character of your local skies. Think about the time of year. The seasons dictate the prevailing weather systems, influencing cloud types and their frequency. The summer months might bring puffy cumulus clouds, while winter might present a more somber sky draped with layers of stratus. Even the time of day affects what you see: morning mist, afternoon thermals, and the dramatic sunsets painted across the evening sky. Take a closer look. Notice the subtle variations in cloud formations. Are they primarily cirrus clouds, high wisps of ice crystals, suggesting fair weather ahead? Or are they lower, denser clouds, hinting at potential precipitation? Each cloud type tells a story, a small piece of the larger atmospheric puzzle. By observing your local skies regularly, you'll begin to notice subtle patterns and trends. You'll develop an intuitive understanding of the relationship between cloud types and local weather conditions. You'll learn to anticipate changes in the weather based on the appearance of the clouds. This connection to the sky above you, this intimate knowledge of your local weather patterns, is a powerful and enriching experience. It's about becoming a weather watcher, a keen observer of the ever-changing canvas above. It's about appreciating the intricate dance between the atmosphere and the land beneath, a dance that shapes our lives in countless ways. And it all starts with a simple glance upwards, a moment of mindful observation, and a genuine curiosity about the world around you. Our journey through the fascinating world of clouds and meteorology doesn't have to end here. The beauty and complexity of these atmospheric phenomena offer endless opportunities for further exploration and discovery. To help you continue your learning, I'd like to share some valuable resources that can deepen your understanding and appreciation of this captivating subject. For those who prefer the convenience of online access, a wealth of information is available at your fingertips. The National Oceanic and Atmospheric Administration, NOAA, website, a treasure trove of meteorological data and educational resources, provides comprehensive information on weather patterns, climate change, and the science behind cloud formation. Their interactive maps and visualizations bring the science to life, offering a dynamic and engaging learning experience. Similarly, the American Meteorological Society, AMS, website offers a plethora of articles, publications, and educational materials, catering to both the casual enthusiast and the seasoned professional. Explore their resources to delve into the intricacies of atmospheric science and the latest advancements in meteorology. Beyond websites, the world of books offers a more in-depth and contemplative exploration of cloud science. Many excellent titles delve into the history, science, and cultural significance of clouds. From introductory guides perfect for beginners to advanced texts for serious students of meteorology, there's a book to suit every level of interest and expertise. A quick search online will reveal a rich collection of books on cloud physics, weather forecasting, and the impact of clouds on our climate. Consider visiting your local library or bookstore to discover hidden gems and expand your understanding of these atmospheric marvels. Furthermore, many organizations dedicated to weather and climate research offer educational programs and resources. These organizations often host workshops, webinars, and lectures, providing opportunities to learn from leading experts in the field. Connecting with these organizations not only enhances your knowledge, but also fosters a sense of community among individuals who share a passion for meteorology and the wonders of the sky. By actively engaging with these resources, you'll continue to unravel the mysteries of clouds and deepen your appreciation for the intricate workings of our atmosphere. The journey of learning about clouds and meteorology is a lifelong pursuit. With a vast array of resources available, you can continue to explore this fascinating field at your own pace, enriching your understanding of the world around you and fostering a deeper appreciation for the wonders of nature. So, continue to explore, continue to learn, and continue to be amazed by the ever-changing spectacle of the skies above. As we conclude our exploration of the captivating world of clouds and meteorology, I invite you to join a vibrant community of cloud enthusiasts and weather aficionados, sharing observations, insights, and a passion for the atmospheric wonders above is a rewarding experience, fostering a sense of connection with like-minded individuals across the globe. The digital age offers numerous avenues for participation and engagement. Social media platforms, such as Twitter, Instagram, and Facebook, host active communities dedicated to meteorology and cloud appreciation. Search for relevant hashtags like hashtag cloudwatching, hashtag meteorology, or hashtag weather photography to discover a wealth of stunning images, insightful discussions, and fascinating facts shared by passionate individuals. Join these conversations, share your own cloud photos, and engage in discussions about the science and beauty of atmospheric phenomena. You'll be surprised by the breadth of knowledge and the enthusiastic spirit of the community. Beyond social media, online forums and discussion groups provide a platform for in-depth conversations and knowledge sharing. These platforms often feature experts and enthusiasts who readily offer guidance and support to those seeking to deepen their understanding of meteorology. Ask questions, share your observations, and engage in thoughtful discussions about specific cloud formations, weather patterns, or the science behind atmospheric processes. You might even discover hidden talents or develop new perspectives on the subject through interaction with this community. Remember that even casual cloud observation contributes to a broader understanding of our atmospheric environment. Sharing your local weather observations or the type of clouds you see, the timing of precipitation, or the impact of weather patterns on your surroundings enriches the collective knowledge and helps build a more comprehensive picture of global weather patterns. These contributions, however small they might seem, play a vital role in advancing our understanding of meteorology and climate science. By participating in these online communities, you become an active member of a global network dedicated to unraveling the mysteries of the sky. Your observations, insights, and questions contribute to a shared understanding of atmospheric phenomena, enriching our collective knowledge and fostering a deeper appreciation for the ever-changing canvas above us. So, join the conversation, share your passion, and let's collectively explore the wonders of clouds and meteorology together. The sky, after all, is the limit. Our journey through the fascinating world of clouds and meteorology is nearing its end. But the exploration doesn't have to stop here. Indeed, the beauty and complexity of the skies above offer endless opportunities for continued learning and engagement. Perhaps you've been inspired to delve deeper into the science behind cloud formation, or maybe you've simply discovered a newfound appreciation for the ever-changing canvas above. Whatever your takeaway, I encourage you to embrace your inner cloud enthusiast. There are countless ways to continue your exploration. Consider purchasing a comprehensive guide to cloud identification, a fantastic resource for expanding your knowledge and refining your observational skills. Many excellent books and websites offer detailed descriptions of different cloud types, their formation processes, and their roles in weather patterns. Armed with this knowledge, your next cloud watching session will transform into a captivating journey of discovery. For those with a more hands-on approach, citizen science projects offer a unique opportunity to contribute directly to meteorological research. Many organizations invite citizen scientists to submit their weather observations, helping researchers gather valuable data on cloud formations, precipitation patterns, and other atmospheric phenomena. Your contributions, no matter how small, contribute to a broader understanding of our climate and weather systems. It's a chance to actively participate in scientific advancement while nurturing your passion for meteorology. Even without formal participation in research projects, you can cultivate a deeper appreciation for the skies above by simply taking the time to observe and reflect. Make it a habit to look up at the clouds, noticing their ever-changing shapes and formations. Try to identify different cloud types and consider how they relate to the weather conditions in your area. Each observation sharpens your observational skills and enhances your understanding of atmospheric processes. Perhaps photography is your passion. Cloud photography offers an exciting creative outlet, capturing the ephemeral beauty of the sky in stunning detail. Experiment with different angles, lighting conditions, and perspectives to capture the unique character of each cloud formation. Sharing your creations online can also inspire others to join this fascinating journey of observation and appreciation. Ultimately, the key is to cultivate a sense of wonder and curiosity about the skies above. Whether you choose to dive deep into the science of meteorology, contribute to citizen science projects, or simply enjoy the aesthetic beauty of the clouds, your continued engagement enriches not only your personal understanding but also our collective appreciation for these magnificent atmospheric wonders. So, keep looking up, keep learning, and keep exploring the breathtaking world of clouds. The journey of discovery is far from over. As we conclude our exploration of the atmospheric wonders above, let's linger for a moment on the sheer magnificence of the cloudscape. Imagine, if you will, a vast, ever-shifting canvas painted across the heavens. This isn't a static masterpiece. It's a dynamic spectacle, constantly evolving under the brushstrokes of wind, temperature, and moisture. Each cloud, a unique brushstroke, contributes to the overall composition, creating a breathtaking panorama that changes with every passing hour, every shift in the atmospheric currents. Picture a sunrise painting the sky with hues of rose and gold, illuminating wispy cirrus clouds that drift like delicate feathers across the dawn. These high-altitude clouds, composed of ice crystals, catch the light, transforming into shimmering ribbons of ethereal beauty. As the sun climbs higher, the canvas shifts, revealing cumulus clouds, their puffy white forms resembling cotton balls scattered across a brilliant blue backdrop. These clouds, born from rising warm air, signal fair weather, promising a day of sunshine and warmth. Later in the day, perhaps the scene transforms. Towering cumulonimbus clouds, dark and imposing, gather on the horizon, their anvil-shaped tops hinting at the potential for rain or even a thunderstorm. These dramatic clouds, symbols of atmospheric power, are a reminder of the dynamic forces at play in our atmosphere. They represent the raw energy of nature, capable of unleashing breathtaking light shows and torrential downpours. Yet, even in their intensity, there is a captivating beauty, a testament to the raw power and artistry of nature. As the sun descends, casting long shadows across the landscape, the clouds take on a new character. They are bathed in the warm glow of the setting sun, their edges tinged with fiery oranges and deep purples. They become silhouettes against the fiery backdrop, their forms softened and romanticized by the fading light. This is a spectacle of ever-changing light and shadow, a reminder of the transient nature of beauty and the constant flux of the atmospheric world. And then, as night settles in, the clouds often transform into a canvas of deep blues and blacks, punctuated by the twinkling lights of distant stars. The moon, a silent observer, casts its gentle glow upon the clouds, creating an atmosphere of quiet mystery and celestial wonder. The clouds themselves, now dark and mysterious, hold the promise of rain or the quiet anticipation of a clear, starlit night. The clouds, then, are not just meteorological phenomena. They are artistic expressions of atmospheric processes, a constant reminder of the dynamic beauty and power of nature. They are a testament to the ever-changing canvas above, a spectacle that unfolds daily, offering a unique and awe-inspiring display of nature's artistry. So, let us continue to look up, to marvel at this ever-changing masterpiece, and to appreciate the wonder of the clouds.